All right, let's talk about machine learning. Drawing a line to separate two groups of data. Seems pretty simple, right? But what if you wanted to find the absolute best line? Well, that's a whole different ballgame. Today, we're going to dive into something called the support vector machine, or SVM for short. And trust me, this model is obsessed with finding that one perfect boundary. So here's our game plan. We'll start with this idea of the widest street. Then we'll properly meet the SVM and check out its secret weapons. We're even going to put it head-to-head with a classic, logistic regression. And finally, we'll wrap up with a practical guide on when you should actually use this thing. Okay, so before we get into all the technical stuff, let's really get a feel for the fundamental problem that SVMs were created to solve. Okay, so take a look at this. We've got two clusters of dots, right? You and I, we could draw, I don't know, a million different lines to split them up. But which one is actually the best one? Think about it. A line that just barely scrapes by one of the groups feels kind of risky, doesn't it? One new piece of data comes along and boom, your whole classification could be wrong. And that exact challenge is what SVMs were built for. So, how do you find that best line? Well, that's where the support vector machine comes in. This isn't a model that just settles for good enough. No, it's on a mission to find the most solid, stable boundary possible. And how does it do that? Honestly, the core idea is just beautiful. Instead of just drawing a thin line, an SVM's whole goal is to find the line that creates the widest possible streets between the two groups. This big empty space is what we call the margin. By making that margin as wide as it can be, the SVM creates a boundary that's as far away from both sides as possible. It's just inherently more robust. And here's where the SVM really starts to differ from other models, like, say, logistic regression. Logistic regression kind of looks at all the data points to make its decision, but the SVM, it's a total minimalist. It literally only cares about the points that are right on the edge of that street, the ones that are closest to the other team. It completely ignores all the easy points way back in their own territory. This unique way of looking at the problem gives the SVM some really powerful tools in its toolkit. So let's break down the secret weapons that make it all work. First up, you're going to hear the word hyperplane. It sounds super complicated, but it's really not. It's just the fancy technical name for the decision boundary. Here, in 2 dimensions, it's just a line. If we were in 3D, it would be a flat plane. Anything more than that, we just call it a hyperplane. It's the wall separating our two groups. That's it. Next up is the margin, and this goes right back to our widest street idea. The margin is that empty space, that buffer zone between our hyperplane and the nearest data points on either side. The whole point of the SVM is to make this margin, this street, as wide as possible. A wider margin means a more confident, more stable classification. Simple as that. And that leads us to maybe the most important concept of all, the support vectors. These are the most critical players in the whole game. They are the actual data points that are sitting right on the edge of the margin. They're the toughest points to classify. You know why they're called support vectors? Because they alone support the position of the hyperplane. Seriously, if you moved one of these points, the entire boundary line would have to move with it. But if you moved any other point, the line wouldn't budge an inch. Okay, but what happens when your data is messy? What if it's all tangled up and you can't just draw a straight line to separate it? This is where the SVM pulls out its killer move, its most famous secret weapon, the kernel trick. It's a totally brilliant way to handle complex, nonlinear data. So here's the magic. Instead of trying to draw some crazy curvy line in our 2D space, the kernel trick essentially pretends to project the data into a higher dimension, say 3D. And all of a sudden, what looked like a tangled mess can now be split perfectly by a simple, flat plane. And the most amazing part, it does all this with some clever math without actually doing the heavy computational work of transforming the data. This lets us use different kernels, like the RBF kernel for creating these complex, swirling boundaries, or a polynomial kernel for more general curves. It's incredibly powerful. All right, enough theory. Let's see this thing in action. It's time for a showdown between our SVM and an old favorite, logistic regression. And for our battleground, we're using the classic iris flower dataset. It's a famous problem in machine learning. The goal is simple. Classify different species of iris flowers based on things like their petal length and width. It's the perfect test for a classification model. And the results are in. For this specific task, the support vector machine, using that RBF kernel we just talked about, came in at around 98% accuracy. Pretty impressive. Logistic regression did well, don't get me wrong, but it was just a little bit lower. So in this face-off, the SVM takes the win. So why did it win? Well, this really gets to the heart of the SVM's strength. SVMs are the champion when what you care about is having a really clear, wide margin, not just getting a probability score. That RBF kernel allowed the SVM to draw a flexible, swirling boundary that perfectly wrapped around the data clusters. A simple straight line from logistic regression just couldn't compete with that shape. It's all about picking the right tool for the job. Which brings us to our final and maybe most important section. After seeing all this, when should you actually pull an SVM out of your toolbox for your own projects? So let's break it down. SVMs really shine when you have high-dimensional data. We're talking things like text classification or image recognition. They're also amazing when there's a pretty clear separation between your classes. On the flip side, they can be pretty slow to train on really huge, messy data sets. And if what you really need are actual probability scores for your predictions, something like logistic regression is probably a better bet. So if you're going to remember one thing, let it be this. The SVM's superpower is its intense focus. By zeroing in on only the most difficult data points, those support vectors, it builds a decision boundary that is as robust and as confident as possible. It's not just finding any old line, it's finding the best, widest, most stable street it can carve out between your data. And that leaves us with one final question for you to think about. Next time you're facing a classification problem, ask yourself, is a good enough line that gets the job done okay for me, or does my problem demand the most robust, most confident boundary I can possibly find? Your answer to that question will tell you if an SVM is the hero